Hello, my dear students. Here in this lecture, I am going to discuss about the factors affecting the modes of vibrational frequency or wave number. I, Mrs. Hemlata Nimje, Assistant Professor in JSPM Charak College of Pharmacy and Research, Wagholi, Pune. The various factors which are affecting on the vibrational frequency from their normal values are Fermi resonance, then hydrogen bonding, electronic effects, bond strength, and field effect. Now we see that some basic value of some functional group like OH, which has 3600 centimeter inverse, NH 34, CH 33. So likewise, these are the some functional group that you have to remember the values. These are the basic values that you have to remember while studying the factors affecting on infrared spectroscopy or their vibrations modes. Now first factor, coupling vibration or Fermi resonance. So first of all, we will discuss about what is coupling resonance and Fermi resonance. Here see an example of methylene or methyl group, that is CH bond has only one stretching vibrational frequency, where the methylene group shows a two stretching vibration frequency which include symmetric as well as asymmetric vibration. Because of the mechanical coupling or interaction in between the CH stretching vibration in the CH2 group. So asymmetric vibration occurs at higher frequency or wave number than the symmetric vibration. These are known as coupling vibration because this vibration occurs at a different frequency than that required for the isolation of the CH stretching. Now see, this is the example of the CH stretching, how it will shows the two stretching symmetric as well as asymmetric. You can see that this is symmetric vibration which has 2872 and asymmetric vibration 2962, which is somewhat increased as compared to symmetric vibration. So this is because of the presence of the two atoms to the single bond, which will shows a symmetric as well as asymmetric vibration. So in same condition in methylene group, we can see that there are two type of vibrations, so that the single peak is divided into the two peak near about the different vibrational frequency, symmetric as well as asymmetric. That's why it is called as coupling vibration. Similarly, in the case of bending vibration, which is occur at about 1400 near about 1400 centimeter inverse, there shows an overlapping of the two peak in some case, or it may be shows a two peak. That's why you have to remember these are called coupling vibration. Now resonance means what? In Fermi resonance, this resonance term indicate a vibration of large amplitude produced by the relatively small vibration. That means a coupling of the two fundamental vibration modes produce the two new modes of vibration with the frequencies higher and lower than that observed in the absence of interaction. The interaction can also take place in between the fundamental vibration and overtone or combination tone vibration, and such interactions are called as Fermi resonance. If two different vibrational levels belonging to the same species have nearly the same energy, that means shifting of one toward the lower and other toward the higher frequency may occur. So resonance, we can consider this example so you can understand properly. In case of anhydride, there are two carbonyl group. In that, this pi electron will be shifted to this oxygen, so that it get a negative and positive charge due to the resonance. Similarly in this case, so what, due to this resonance there is a formation of the two peaks, 1810 and another will be 1760. So single peak of carbonyl group which is at about 1700, which is divided into the two peak. This is due to the resonance in between this carbonyl group and oxygen. Similarly in the case of amine, especially primary amine, because primary amine itself contains two hydrogen which is attached to the single nitrogen. So in this primary amines, there are two type of symmetric and asymmetric vibration take place, so that the single peak of this NH2 will divide it into the two peak, and that's why it shows a Fermi resonance. So near about 3300 symmetric and 3400 it is asymmetric peak you will observe. So you can see that this is the curve in that NH2 will shows a 2 peak in case of this primary amine. If this example is related to the secondary amine, this peak will not shows here. Why? Because the nitrogen is have only single hydrogen in secondary amine, so that it will shows this Fermi resonance in only the nitrogen which is primary. That's why it will be divided into the two peak. So you can see that these are the two peak. One is symmetric and another is asymmetric. Another factor which are affecting in higher vibration modes, that is hydrogen bonding. What exactly it is? The hydrogen bonding is generally related with the OH, or it is related with the NH. Stronger the hydrogen bond, the longer the OH, the lower the vibration frequency, and broader and more intense will be absorption band. Similarly, in case of NH, stretching frequency of amines are also affected by hydrogen bonding as that of hydroxyl group, but the frequency shift from amines are lesser than that of for hydroxy group, because the nitrogen is less electronegative and the oxygen as compared to oxygen, so that the hydrogen bonding in the amine is weaker as compared to the hydroxy compound. Generally, we know that hydrogen bonding, there are two type bonding, intermolecular hydrogen as well as intramolecular. So intermolecular hydrogen bonding give rise to broad bands, while intramolecular hydrogen bonding give like a sharp and well defined band. And inter and intramolecular bonding can be distinguished with the help of dilution. We'll see the examples. Now in this you can see that OH stretching, that is hydrogen bonding, will form, and it will shows a sharp as well as the broad peak in near about 36 to 3300 centimeter inverse. Now we can see that how the intermolecular and intramolecular hydrogen bonding is there. This is intramolecular hydrogen bonding, the bonding between the two different molecules. This is one molecule, this is another molecule of alcohol, ROH. So here there is a bonding which is having the long bond as compared to the intermolecular hydrogen bonding. So intermolecular hydrogen bonding, the bonding which is formed within the molecule itself. So these are the two bonds which will shows a broad or the sharp peak due to this. The many you can see that many kinds of hydroxy OH bonds of different length and different strength. This leads to the broad band. Always remember the OH or hydroxy group which is present in the compound, and if it is concentrated solution, then it will always shows a broad spectrum. Okay, now another example, you can see that ROH, which is having a very dilute solution. So in this dilute solution of CCl4, there is a free OH group is present, so that distinct bond has a well defined length and strength is available. So solvents are surrounding to that OH, and so do not have the hydrogen bonding. So in this case we can find the broad peak. Now we can see that how the peak will observe in a different form of concentration which containing the hydroxy functional group. Now see, the intermolecular hydrogen bonding remains unaffected on dilution, and as a result the absorption band also remains unaffected, whereas the intermolecular bonds are broken on the dilution and there is a decrease in the bonding of OH. Now see, in the pure liquid we can observe that there is a broad peak in the pure liquid. In case of dilute solution, there is a broad peak along with the some OH group is free, which will shows a sharp peak. And in case of free OH group, which is having no broad peak, so that it will shows it doesn't show any type of the broad peak here, so that the we can say that the compound which contain hydroxy group, it will shows a broad peak as well as sharp peak. but if it is very dilute solution, there will be no hydrogen bonding. So from this we can interpret the presence of the OH. We can easily understand this example with the help of cyclohexanol, which is having OH functional group. You can see here is the broad band. In this broad band, and in the butanoic acid, it is also showing a broad band having the hydrogen hydroxy group, which form a hydrogen bonding. So this will shows in near about the 32 to 2700 centimeter Hinver. So another effect which will affect onto the vibrational frequency is the electronic effect. In that, the change in the vibration frequency for a particular group take place when the substituents in the neighborhood of that particular group are changed. It includes inductive effect, mesomeric effect, and field effect. We'll see one by one. Due to above force constant and the bond strength, it changes and change in the wave number and frequency. So first we will discuss about the inductive effect, how it will affect onto the vibrational frequency. Now we'll see about the functional group of carbonyl group. Here the carbonyl group having the frequency of absorption near about 1700. But due to the presence of R group here in case of A and B, in B there is a X, which is electron withdrawing group. R is the electron releasing group. So due to the presence of the neighboring group, which is electron releasing, it lowers its absorption frequency and weakens the carbonyl group. While in case of B example, the electron withdrawing group X is present, so that it strengthens the carbonyl bond and rises their absorption frequency. So this is the example of inductive effect. You can easily understand. After that, what is exactly positive inductive effect and negative inductive effect? The introduction of alkyl group causes positive effect, which results in the lengthening or weakening of the bond. Hence, the force constant is lower and wave number of absorption decreases. Let us compare the wave number of carbonyl group to the following examples. In case of formaldehyde, the carbonyl group has 1750 centimeter inverse. But see the acetaldehyde, as the CH3 is an electron releasing group, their frequency is somewhat decreases 1745. In acetone, one more releasing group is attached, that is CH3 methyl group. The frequency is further decreases. So we can say that as the electron releasing group attached to the functional group, their frequency will be decreases from their base values. Introduction of electronegative group or group which gives a negative effect, which results in the bond order to increase. Hence, the force constant increases and the wave number of absorption will rises. Now, we can see that this example, conjugation is also affect the absorption mode. It may increase or decrease. If you increases the conjugation in any type of the compound, that is also affect onto the frequency of absorption. Say for example, this is a carbonyl group which is a simple ketone, and this is a carbonyl group which is alpha beta unsaturated alkene is attached to this compound. So in this case, as there is a double bond, it will shift to here their electron and forms conjugation. Due to the conjugation, they weakens their carbonyl group and frequency is lower. So as we can say that similar in case of alkene, there is a two double bond and there is a single double bond, which shows a decrease in the frequency, because the C double bond C is having 1600 near about frequency of absorption, and their frequency will increase in single bond and decrease in the two double bonds of the compound. That indicates, these two examples will shows that as there is an increase in the conjugation, the frequency of absorption will be lower. Conjugation lower the frequency of carbonyl group and also of the C double bond C. This is the example how it will lowers the strength of the carbonyl group. Now see this example which contain carbonyl group and double bond at the position of alpha beta. In this case, this electrons are shifted to the carbon, and due to this the oxygen is having negatively charged and this carbon is having positively charged. So that if we see the functional group of carbonyl compound in IR absorption, if it is attached with the 2R, that is alkyl group, it has a 1715. And if there is an additional alkene, that is double bond is present, that means conjugation, their frequency is decreases, that is 1690. So this you have to remember ki how the compound frequency is lower or higher due to the presence of the carbonyl group. Now how these factors will affect onto the carbonyl group frequency. The carbonyl group containing different compounds, we have to take an examples of acyl chloride, ester, aldehyde, ketone, carboxylic acid, amide. In all these compounds, carbonyl group is present. Now we'll see the first compound. There is a Cl is attached, so their frequency is 18. As it is replaced by OR, their frequency decreases. As a hydrogen, further decreases. Releasing group R, there further decreases. Then hydrogen bonding, which lowers the bond, then further decreases. Then NH2, which has a further hydrogen bonding, which is further decreases. Means you can see this all example are, we are dealing with the same functional group, that is carbonyl group, which has a basic value of 170. But somewhere it is decreases and somewhere it is increases due to the presence of the neighboring group, and this group will affect on the absorption of IR. So remember these things, while any functional group, when you consider their absorption, it may decrease or increases due to the presence of the neighboring group. If it is withdrawing group, their frequencies increases, and if there is electron releasing group, their frequency of functional group is increases. So these are the example. Now we'll shift to the mesomeric effect. What it is? It causes due to the lengthening of this lengthening or the weakening of the bond, which leads to the lowering of the absorption. Example, methyl benzoate and methylamide. In methyl benzoate, there is a oxygen near about the carbonyl group, and here the nitrogen near about the carbonyl group. So due to the less electronegativity of the nitrogen, it has a lower absorption. High negativity of the oxygen, it has a higher absorption. So that here the conjugation is one of the most factor which will affect. So here the more greater conjugation as compared to this methyl benzoate. So their frequencies increases or decreases. Next, resonance effect in this case similar like a conjugation, which will lower its absorption, and if there is a hydrogen bonding if present near about carbonyl group, there also lowers its absorption. See, this is an example of IR spectra for carbonyl functional group. This carbonyl functional group is having 1730, which has aldehyde, and this is an ester functional group. So C double bond C, which has an ester, the frequency is 1740, somewhat increases, and as it is an acetyl chloride type of group, so D-cannonyl chloride, which is having a Cl group, electron withdrawing group. That's why their frequency is increases, that is 1800. So in this way, we have to remember that for a group which is attached, functional group, any functional group can be shift their frequency to the higher or lower due to the presence of the neighboring groups. Bond strength. The bond strength is one of the important factor which affect on the vibrational frequency. See, this is the CH strengthening of the bond. In this case, carbon triple bond, carbon double bond, single bond, they are changes their hybridization. If there is a triple bonded carbon is attached, CH strength or stretching, it changes because of the sp hybridization. If there is a double bond, there is a sp2 hybridization. If there is a single bond of CH which is attached to the single bonded carbon, then it is sp3 hybridization. and if it is in aldehyde, their frequencies further decreases because of the carbonyl group. So CH stretching is depend on the type of the group which is attached. Single bonded has a less S character, double bond has more, and triple bond has a 50% of S character. So that their bond strength has increases as the S character is increases, and so the frequency is increases. So we can see that in aldehyde there is a lowest frequency, that is 2800 centimeter inverse. Then in case of sp3 hybridization it is 3000. Then sp2 hybridization 3100 centimeter inverse, and which is higher in CS stretching when it is attached to the triply bonded carbon. So that's bond strength will affect onto the absorption. Now last effect is a field effect. We'll see what is field effect. In ortho-substituted compound, the lone pair of electrons on the two atoms influence each other through a space interaction and change the vibrational frequency of both the group. This effect is called field effect. The two group affects the vibration frequency by steric interaction or electrostatic force. Now see, this is an example of acetopenone where the X is the any type of substitution. Ortho substitution, it may be any halide, Cl, Br or F, which will affect on the frequency of absorption in between C double bond C. So this will affect due to the steric interaction or electrostatic force, and so that the frequency may be shifted to the higher or lower layer. See, this is the one of the example where the K and 1. In that K is the rotational isomers and it is not an isomer. So that as both the isomers are usually found together, and therefore the two carbonyl here, the carbonyl group in case of K will shows a frequency near about 1700 as compared to their frequency will decrease. So depending upon the steric interaction between the ortho groups, their frequencies increases, and in this case it is a decreases. So steric effect will affect onto the absorption of the functional group. So now we'll already study about all the effect. First Fermi resonance, second hydrogen bonding, third electronic effect, fourth bond strength, and fifth steric interaction. So I think you understand all the factors affecting on infrared spectroscopy. Thank you so much.